Hi and welcome to the 19th part of the C# for Beginners course. In the last tutorial we focused on the object-oriented principle of inheritance. In this tutorial we'll focus on another principle of object-oriented programming, namely polymorphism. If you haven't seen the 18th part of this course comprised of 2 videos on C# inheritance, it is not essential, but I do recommend that you view this video series before watching this video. For your convenience, I've included links to these videos on C# inheritance below in the description. Please like, subscribe, share, comment to support the channel. It will be greatly appreciated. And please smash the bell icon so that you can be notified of future content. Right, so what is polymorphism? Basically, polymorphism is the ability of an object to take on many forms. The object-oriented principle of polymorphism is the provision of a single interface to entities of different types. The word polymorphism has Greek roots and essentially means many shapes, poly meaning many and morph meaning form. It is considered the third pillar of object-oriented programming after encapsulation and inheritance. Polymorphism has 2 distinct aspects. An object at runtime of a derived class type may be defined in a developer's source code as the type from which the derived class inherits. This can be applied in places such as methods and collections. When this occurs, the object's declared type is no longer identical to its runtime type. Base classes may define and implement virtual methods, and derived classes can override them, which means they provide their own definition and implementation. At runtime, when client code calls the method, the CLR or Common Language Runtime looks up the runtime type of the object and invokes that override of the virtual method. This means that in the developer's source code, the developer can call a method on a base class, which means at runtime a derived class's version of the method will be executed. In this tutorial, we are going to first try to understand the basics of polymorphism and the rules associated with the code implementation related to the principle of polymorphism. As you become more au fait with object-oriented principles, the advantages of using encapsulation, inheritance, polymorphism, and abstraction in designing and engineering your applications will become more apparent. Some advantages of using object-oriented principles in software engineering include reuse of code, easier maintenance of code, and the provision for greater design flexibility and extensibility. Design patterns are beyond the scope of this tutorial, but I'd like to make the point that a fundamental knowledge of object-oriented principles provides a foundation to learn powerful design patterns, for example, the decorator pattern, the strategy pattern, the command pattern, the observer pattern, and the iterator pattern, just to name a few. The mnemonic acronym SOLID provides an excellent framework to understand how to engineer your code to achieve better, maintainable, and flexible designs when applying object-oriented principles to software engineering. The details of SOLID are beyond the scope of this tutorial, but here's a basic outline. So the S in SOLID stands for Single Responsibility Principle. A class should only have a single responsibility, that is, only changes to one part of the software specification should be able to affect the specification of the class. O stands for Open-Closed Principle. Software entities should be open for extension but closed for modification. L stands for Lishkov's Substitution Principle. Objects in a program should be replaceable with instances of their subtypes without altering the correctness of that program. I stands for Interface Segregation Principle. Many client-specific interfaces are better than one general-purpose interface. D stands for Dependency Inversion Principle. One should depend on abstractions, not concretions. Note that all classes in C# are polymorphic because they all inherit from the system.object class. We demonstrated this in the second part of the previous tutorial on C# inheritance, where we implemented our own version of the system.object class's toString method by overriding this method. So let's look at code examples to clarify the effect of polymorphism and the rules of which we should be cognizant of when implementing polymorphism in our code. I'm going to first create a console application .NET Core project in Visual Studio 2019. The code examples I'm going to use to demonstrate rules associated with polymorphism are going to be very simplistic, because the goal here is to understand polymorphism before implementing this object-oriented principle for practical use. So let's create a base class and call it productBase. Let's implement a method for this class named getPrice. This method must contain the virtual keyword so that any derived class can override the getPrice implementation in the base class with code specific to the requirement of the derived class. This method simply returns a decimal value of 10.00. Notice the M suffix included at the end of the numeric literal value. As discussed in previous tutorials, if the M suffix is not included when assigning a literal numeric value that contains a fractal part to a variable of the decimal type, the C# compiler will infer that the numeric type is of type double. This will flag a compile time error. The M suffix explicitly tells the C# compiler that the relevant literal value is of type decimal, and this will prevent a compile time error from occurring. Okay, so let's create a derived class. In the interests of simplicity, let's name this class productDerived. Let's include a colon followed by the base class name, i.e. the base class from which this derived class inherits, namely productBase. So let's provide a specialized implementation for the getPrice method for the productDerived class. Again, we want to keep the code in these examples as simple as possible so that we can clearly focus on the object-oriented principle of polymorphism. So the implementation for the getPrice method in the productDerived class simply calls its base class getPrice method through the use of the base keyword and then adds the numeric literal value of 2 to the value returned from the base class's getPrice method. Notice we do not need to add the M suffix to the literal numeric value of 2 because we have not included a fractal part in this value, which would have meant including a full stop followed by the numeric values representing the fractal part of the value. So we currently have a base class named productBase and a derived class named productDerived that inherits from the productBase class. We have implemented a method named getPrice, which returns a decimal value. The definition for the getPrice method in the productBase class contains the virtual keyword, which allows for any derived class to override the getPrice method and provide its own specialist implementation for the method. We have done this by including the override keyword in the method definition of the productDerived class's version of the getPrice method. The code implementation in the productDerived class's getPrice method simply adds the literal value of 2 to the value returned by the base class's getPrice method. Let's add another class named productAnotherDerived and write code so that the productAnotherDerived class inherits from the productDerived class. Let's create a specialist implementation for the productAnotherDerived class's getPrice method by using the override keyword in its method definition and adding a numeric literal value to the value returned by the productDerived class's version of the getPrice method. The productBase class is at the top of this inheritance hierarchy. The next level of the inheritance hierarchy is occupied by the productDerived class, and the last level of the inheritance hierarchy is occupied by the productAnotherDerived class. So let's go to the main method and write code examples to explore the rules that we must adhere to when implementing polymorphism in our C# code. Firstly, let's write code to instantiate an object from the productDerived class. So this code does not implement polymorphism because we are defining variable p as productDerived, which as you can see is expressed in code as productDerived p. Then we are instantiating an object of the same type, i.e. productDerived, which is denoted by the code equals new productDerived followed by empty brackets. So this line of code does not implement polymorphism because the variable p is defined as the same type as the object that will be instantiated at runtime. Polymorphism occurs when an object instantiated at runtime is of a different type to the type used to define the object's variable in the corresponding source code. Let's run the code. And as expected, the productDerived class's implementation of the getPrice method is executed. The result of 12 is written to the console screen, which is calculated from the returned value from the base class, a value of 10, added to the literal value of 2, which has been coded in the product derived class's version of the getPrice method. A value of 12 is therefore written to the console screen, which is clear evidence that the product derived class's implementation of the getPrice method has been executed to produce the result of 12. So we've just run code where polymorphism has not taken place, because the type defined for variable p in the source code has not changed at runtime. So let's change this code to implement an example where polymorphism will take place. Let's change the type definition for variable p from product derived to product base. Let's leave the object instantiation code as it is. This will in effect mean that the variable p, now defined in the source code as the product base type, will be instantiated as an object of type product derived at runtime. The source code type for variable p is different from the type of object that will be instantiated for variable p at runtime. Both the product base class and the product derived class implement a method named getPrice, so the code where the getPrice method is called on the p variable does not need to change. Product base and product derived share a common interface. So in this example, we have successfully implemented polymorphism. The method getPrice can get invoked on an object of type product base or product derived at runtime. These types share the same interface but have different implementations of the getPrice method. One object can be used to invoke more than one implementation of an interface. In this example, the product derived class overrides the getPrice method through the use of the override keyword, which means that in this example, the derived class's version of the getPrice method is executed at runtime. So what happens if we change the type definition for variable p from product base to product another derived in our source code? The result is Visual Studio underlines the instantiation part of this line of code with a red squiggly line. So the new product derived code, i.e. the code that instantiates an object at runtime, is underlined with a red squiggly line. Let's hover our mouse pointers over the red squiggly line and see what the compile time error message states. So it seems clear that the rule here is that we are able to instantiate an object of a type that exists at a higher level in the inheritance hierarchy or at the same level in the inheritance hierarchy when compared to the type that defines the variable that references the object in the relevant source code. But it is not acceptable to instantiate an object that is defined in source code with a type lower down in the inheritance hierarchy when compared to the type of the instantiated object. As you can see, we have attempted to do that in this example, and the result is that a compile time error is flagged. So let's test this rule once again, and this time let's define the variable p as product derived, and attempt to instantiate an object of type product base. Essentially, the same compile time error is flagged, and if we hover our mouse pointers over the red squiggly line, essentially the same error message is presented. So let's define variable p as product derived and instantiate an object of the same type. And let's also explicitly convert the instantiated object, which will be the type product derived, to type product base. Note that product base is higher up in the inheritance hierarchy than product derived. Let's run the code. So clearly the explicit conversion has had no effect on which version of the getPrice method is executed. The result is 12, which means that the product derived class's version of the getPrice method was executed. This is because the override keyword has been used in the definition of the getPrice method in the product derived class to override the product base class's counterpart method, which is marked with the virtual keyword. The common language runtime will always seek the last overridden version of the method to execute. So although the explicit conversion from product derived to product base is valid, the product base class's version of the getPrice method is not executed. The product derived class's version of the getPrice method is executed because it is the last overridden implementation of the method when looking at the relevant classes involved in this code, i.e. product base and product derived. Right, let's see what happens if we explicitly convert variable p to the product another derived type. Let's run the code. And this has resulted in a runtime error. The error essentially states unable to cast object of type product derived to type product another derived. Let's define P as product base and run the code. So here product P is initially defined as product base. At runtime, an object of type product derived is instantiated. This is all perfectly alright, but then we are attempting, as in the previous example, to explicitly convert the object stored for variable P to type product another derived. Essentially, this results in the same runtime error we received in the previous example. Let's prove this once again with another example. Let's instantiate an object of type product base and try to explicitly convert the object to type product derived at runtime. And once again, we essentially get the same runtime error. Let's try to convert the object from product base to product another derived. And once again, we essentially get the same runtime error. So let's discuss the significance of the new keyword in the context of applying this keyword to method definitions. If you'll recall, we have already tested what happens when we run the following code. Product derived P equals to new product derived. But in this example, we are explicitly converting variable P from product derived to product base, and then writing the result of the getPrice method executed on the object stored for variable P to the console screen. Even though this code successfully converts the object stored for variable P from product derived to product base, the version of the getPrice method implemented in the product derived class is executed. It seems to me that if we were to do an explicit conversion from product derived to product base, as is the case in this example, our intention must be to run the code implemented for the getPrice method in the product base class. So in order to achieve this, we need to remove the override keyword in the product derived class's method definition for the getPrice method and replace the override keyword with the new keyword. And let's do the same in the product another derived class to avoid a compile time error. Let's run the code. And the result returned by the getPrice method is 10, meaning that the intended version of the getPrice method has now been run, namely the version implemented in the product base class. And what happens if we define variable P as product base in our source code, but instantiate it as the product derived object type at runtime? If you'll recall, we have tested this in a previous example, and the result was that the version of the getPrice method in the product derived class was executed. This is because previously we were using the override keyword in the getPrice method definition in the product derived class. We have now replaced the override keyword in the getPrice method definition in the product derived class with the new keyword. Let's run the code. And the result reveals that the version of the getPrice method in the product base class has been executed. For good measure, let's replace the new keyword in the method definition for the product derived class with the override keyword and run the code. And this is an expected result. The version of the getPrice method in the product derived class is executed. Let's replace the override keyword in the getPrice method definition in the product derived class with the new keyword. And let's replace the new keyword in the getPrice method definition in the product another derived class with the override keyword. Right, as you can see, the C# compiler has flagged a compile time error. You can see a red squiggly line under the getPrice method version in the product another derived class. So clearly there is a rule that you are not able to override a method marked with the new keyword. So let's replace the new keyword with the override keyword for the definition of the getPrice method in the product derived class to address the compile time error. Not only are you able to override a method marked with the virtual keyword, you are also able to override a method marked with the override keyword. So let's now implement a scenario where the P variable is defined in the source code as product base and instantiated at runtime as an object type product another derived. Let's test the code. And the version of the getPrice method that is run is the version that resides in the product and other derived class. The common language runtime has found the last overridden version of the getPrice method in the inheritance hierarchy and executed this version of the method. And if we try to explicitly convert the object stored for variable p from product and other derived to types higher up in the inheritance hierarchy, namely product derived and product base, the version of the getPrice method in the product and other derived is still executed. The override keyword directs the common language runtime to find the last overridden version of the method, i.e., the version of the getPrice method that must be executed. So let's replace the override keyword in the product and other derived classes definition of the getPrice method with the new keyword and run the code. And now the version of the getPrice method in the product derived class is executed. Let's change all versions of the getPrice method in the inheritance hierarchy to include the new keyword instead of the override keyword, except for the product base class's version of the getPrice method, which includes the virtual keyword. If we execute code in the main method that defines the p variable as product base and instantiates an object of type product and other derived, you can see the effect of the new keyword applied to the getPrice method in this way. The version of the getPrice method that is executed is the getPrice method that resides in the product base class, which you'll notice is the type with which we have defined the p variable in our source code. And if we change the type definition for variable p to product derived, now the version of the getPrice method that is executed is the one that resides in the product derived class. Let's see if the same rule applies when we define variable p as product and other derived, and it does. So, we have clearly seen from these examples how we can implement polymorphism in our code through the use of an inheritance hierarchy and the virtual, new, and override keywords. We have also seen through these examples the different effects caused when applying the new keyword to method definitions or applying the override keyword to method definitions. There are two other C# keywords I'd like to discuss in relation to object-oriented programming, namely the abstract keyword and the sealed keyword. We are going to demonstrate how these two keywords can be applied to both class definitions and method definitions. We will then discuss the effect that these two keywords have on object-oriented program design. So let's apply the abstract keyword to the product base class. As discussed in previous tutorials, this means that we are now unable to instantiate an object directly from the product base class because it is now an abstract class. In order for client calling code to consume code within the product base class, code must be executed on an object instantiated from a class that inherits from the product base class. So we can create a method in this abstract class and include the abstract keyword as part of the method's method definition, and this method returns a string. Note, a method marked with the abstract keyword cannot implement code. An abstract method only serves as a method definition. You'll notice a red squiggly line appears under the product-derived class name. An abstract method does not contain any implementation, so a class that inherits from the abstract class in which the abstract method resides has a responsibility to implement code for the abstract method. So if we click Show Potential Fixes, then Implement Abstract Class, you'll see that Visual Studio creates a default implementation for the getProductName method in the product-derived class. And notice that the newly created getProductName method contains the override keyword in its method definition. Note, we must include the override keyword when implementing code for an abstract method. So for this method, let's simply implement code that returns the name of the class, product-derived, as a string. And we are not obliged to have any implementation for this method in the product and other derived class. But we can do this if we choose, because the getProductName method in the derived class contains the override keyword as part of its method definition. So let's override the getProductName method in the product and other derived class. The code implementation for this method will simply return the name of the class in which it resides. But now what happens if we apply the sealed keyword to the getProductName method in the product-derived class? Well, as you can see, red squiggly lines have appeared under the implementation of the getProductName method in the product and other derived class. The sealed keyword applied to a method in a base class serves to prevent a class that inherits from the base class from being able to override the sealed method. You are also able to apply the sealed keyword as part of the class definition, like this. This means that other classes cannot inherit from this class. So now that we have gone over some fundamental rules associated with implementing polymorphism in our code, let's create a more substantial example demonstrating the implementation of polymorphism applied in C# code. I'm going to create 3 classes. Each class inherits from a base class named shape. The shape base class contains a method named draw. Each class that inherits from the shape base class will contain its own implementation of the draw method. So the shapes we wish to draw to the screen in our application are a triangle, a rectangle, and a circle. So each class that inherits from the shape base class denotes one of the shapes I've just mentioned. I'm going to go through this code fairly quickly because the focus of this tutorial is on polymorphism and not the implementation detail that performs the function of outputting the shapes to the console screen. So there's no need to follow along with the implementation of the code while watching this part of the tutorial. I do, however, recommend that you download the code for this example from GitHub. A link to the relevant repository is available below in the description. I'll create a class named shape, which will serve as the base class in this application. I'll apply some temporary implementation for a method named draw. This method does not accept any parameters and does not return a value. The next class to create is named triangle. Let's apply code so that the triangle class inherits from the shape class. Let's override the draw method and implement code that outputs a triangle shape to the console screen. Let's instantiate a triangle object in the main method and apply code that calls the draw method on the instantiated object. Let's test the code. Great! Let's then create a class named rectangle and apply code so that the rectangle class inherits from the shape class. Let's override the draw method in the rectangle class and implement code for this version of the draw method that outputs a rectangle to the console screen. Let's test the code for the rectangle class. Excellent. Let's now create a class named circle. Let's write the code so that the circle class inherits from the shape class. Let's override the draw method and write the code that will output a circle to the console screen. Right, let's test the code for the circle class. Great. So now I'm going to create a static method that contains code to enable a user to choose the shape to output to the console screen. Okay, notice how we are able to check whether the variable named shape is referencing a null value through the use of a simple if statement before attempting to execute a method that belongs to the object. C# allows us to use a question mark followed by a full stop, then the name of the method we wish to execute on the object, like this. Applying this code will mean that at runtime, an attempt to execute the method will only occur if the object of which this method is a member is not null. If you attempt to call a method on an object that is null, a runtime error will occur. Writing the code like this means we have achieved the necessary null check without the need to write extra conditional code. Let's test this. If I press 1, great. If I press 2, great. If I press 3, excellent. And if I press 4, the code implemented in the base class's draw method is executed, which at the moment only contains temporary code outputting the text not implemented. I'm going to implement code in the shape base class's draw method to output all the shapes in this application to the console screen at once. Let's test the code. And now if we press 4 to execute the draw method version that resides in the shape base class, we can see all the shapes outputted to the console screen, which is the intended result. Excellent. So, one interface, many forms. Poly meaning many, morph meaning form. We demonstrated that polymorphism occurs for an object when it is defined as one type in source code and then instantiated as another type at runtime. We demonstrated that polymorphism can occur when an object of a specific type is converted to another type at runtime. We demonstrated that through polymorphism, one object can have one interface and also have multiple implementations of one interface. This is the essence of polymorphism. We looked at the rules that must be adhered to when implementing polymorphism in source code to prevent compile time or runtime errors. We demonstrated the use of the override and new keywords, and how the application of these two keywords on method definitions can cause different polymorphic effects for objects. We briefly looked at the effect of the abstract and sealed keywords when applied in an object-oriented designed application. Lastly, we demonstrated through the shapes code example how one interface can be reused for multiple concrete implementations. In the next tutorial, which will be the 20th part of the C# for Beginners course, we'll focus on the use of interfaces in C#. Please like, subscribe, share, comment to support the channel. It will be greatly appreciated. And please smash the bell icon so as not to miss out on future content, which will be coming soon. Please download code examples from GitHub. A link to the relevant repository has been included below in the description. Thank you and take care.